Now let us apply the Gauss law to calculate the electric field due to a point charge. Consider a point charge Q. Now draw a spherical surface of radius R with the point charge at the center of the sphere. The electric field E is along the radial direction pointing away from the center and is normal to the surface of the sphere at every point. Now consider a small element del S. Oh, sorry. This small element called del S that is also pointing normal radially outwards. Now, the normal to the element of area del S is parallel to E. According to Gauss law, we know that phi E is equal to Q by epsilon naught. Now, what is phi E? According to Gauss law, phi E is Q by epsilon. Now, let's calculate for this sphere. The total flux of this sphere is E into 4 pi r square. And since they are parallel to each other, angle between E and LS is 0. So cos theta is 0. This is first. Now substituting 1 on 2, we get that Q by epsilon is equal to 4 pi r square. Oh, into, I forgot the E. So E is equal to Q by 4 pi epsilon naught r square. Isn't this the electric field expression for the point charge? So even with the Gauss law, we find the same result. Next, let's calculate the electric field due to a long line charge using Gauss law. A line charge is in the form of thin charged wire of infinite length with a uniform linear charge density phi I. This is charge per unit length. Let there be a charge Q on the wire. So this charge, this is a, will represent this charged wire like this. The charge on wire is Q. We have to calculate the electric field at a point P, which is at a distance R. So let this be the point P we have to calculate. We are going to use Gauss law. So we need a Gaussian surface. Here the cylindrical surface is a Gauss. So draw a right circular cylinder of radius R with the long wire as the axis of the cylinder. So let's draw the cylindrical surface. So this is a cylindrical surface. The cylinder is closed at both the ends. The surface of this cylinder is the Gaussian surface. The magnitude of electric field E is same at every point on the curved surface of the cylinder because all points are at the same distance from charge Y. The electric field direction and the normal to the area element del S are parallel. So we are considering a small element del S. This is del S. And the electric field is also parallel. The length of the cylinder be L. So the total charge enclosed in the cylinder is given by as Q is equal to charge per unit length into length, and area of the curved surface is 2 pi r. For the flat surfaces at the top and bottom of the cylinder, the normal to these areas are perpendicular to the electric field since the cos theta is 0. So these surfaces do not contribute to the total flux. Hence, the flux phi E is given as summation E dot del S, which is E into 2 2 pi Rn. Now we know that from Gauss law, phi is Q by epsilon. Hence, from equation 1 and 2, now what is Q? Phi I into L by epsilon naught. So let's write it here. So E is equal to phi L by epsilon naught into 2 pi R L. So we can calculate this. So E is equal to phi I by 2 pi epsilon naught R. This shows that electric field varies inversely with the distance. Next, let's calculate electric field due to a uniformly charged spherical shell using Gauss law. A spherical shell is a hollow sphere having infinitesimally small thickness. Let this spherical shell be of radius capital R. Carry a total charge Q, which is uniformly distributed on its surface. We shall calculate the electric field due to the spherical charge distribution at 2 points, external as in and internal. First, let's calculate the field at the external point. Let there be a point P external outside of, this is the sphere, right? Outside of the sphere, let there be a point. We will draw a Gaussian surface. Here the Gaussian surface should be closed now, so we are considering a spherical surface that is passing through the point P, and it's concentric with the charge distribution. By symmetry, the electric field is radial and it's pointed outwards. So, uh, oh, this is the radius of this outer sphere. We have to draw the electric field E. It's radially outward, and it's normal to the surface element everywhere. We'll consider the surface element here, that is also del S. Its magnitude at all points on the surface has same value E. Now let's apply the Gauss law. Phi E is equal to, now the total flux is E dot del S. Since E and E and del S are parallel. Cos theta is 0. Sorry, theta is 0, so cos theta is 1. And this will be E dot E into, so we can write this as E del S is the spherical sphere Gaussian surface area, no? So Gaussian surface area, so it's 4 pi r square cos 0 q by epsilon. This is 1. So we get that E is equal to q by 4 pi epsilon naught r square. Wait a minute. I consider a capital Q here, right? So from the result, we can conclude that for a point external to the spherical shell, the entire charge in the shell can be treated as though located at its center. The electric field decreases with distance. Instead of a spherical shell, if we had taken a charged solid conducting sphere, we would have obtained the same result. This is because the charge of a conductor always resides on its outer surface. Now let's calculate electric field at an internal point. So this is our sphere. Of charge Q uniformly distributed around across the surface. Let's draw the Gaussian surface. Let P dash be an internal point, R be the radius of the inner shell. The concentric sphere passes through the point P dash. Consider an element del S normal to the surface. Now what is the electric field? The electric field at an internal point of the shell is 0. Applying the Gauss law, the flux is equal to Q by epsilon naught. So E dot del S component can be written as E into 4 pi r square Q by epsilon naught. Since E is 0, the charge inside the sphere is 0. Therefore, the total electric field is 0. The same result is applicable to charged solid conducting sphere. Next, let's calculate the electric field due to a plane sheet of charge using Gauss law. Consider an infinite plane sheet of charge ABCD. Charged uniformly with surface charge density phi. The electric field will be perpendicular to the sheet, directed away from it. Electric field will be away from it. Now let C be the point in front of the sheet and P dash be the point on the other side. This is where at point P we will be calculating the electric field. So we need to draw a Gaussian surface in the form of cylinder with its axis parallel to the field and one of its circular caps passing through the point P. The other circular cap of the cylinder lies symmetrically opposite with P dash on the outer side of the sheet. This is being situated at same distance as P. Now we'll calculate the electric flux through the both of these circular caps. Since the electric field is perpendicular in the curved surface of the cylinder, we will not find any the E dot del S component will be, the flux will be 0. So we will be calculating the electric flux through the caps. So it is, so, so here this is the E component. Similar to before, we consider a small element del S on the circular cap. So it will be E dot del S on this component, E dot del S in this circular cap. Since the angle between E and del S is 0, cos theta is 1, so we will get 2E del S. So, and since the electric flux through the curved surface is 0, total flux is 2E del S. As the charge enclosed by the Gaussian surface is, we will sing about this thing. Oh, sorry. From Gauss law, we know that Q by epsilon, which is pi del S by epsilon. So equating these two, this is the electric field. It is independent of the distance from the field.